we'll be ready to go. All right. Slideshow from current slide. All right, first I want to know if it's, oh wait, still got to do this. Sorry about this. Hide presenter view. Okay. I think finally we're ready to go now. And for some reason, it's decided to offset, and I do not know why. Sometimes it does, and sometimes it doesn't. But I did want to point something out to you, not that you probably care that much, but left hands, right hands, administrative decisions, I don't know how these things are made. They came in without notifying us at all, and we're the ones who teach here, that they resurfaced the boards, the whiteboards as well as the blackboards. This used to be a chalkboard, okay? And people were finding, I don't use the ink, because I use the ionizing pen on my laptop and project. But people who do use this found that the new surfaces they put on were sometimes really hard to erase. And they were smudging, and people were having to really put a lot of elbow grease and spray a lot to get them. And then they were also coming up some. So people said we didn't want, some that saw what was happening to others said we don't want them in our classrooms. Our boards are fine. And that raised a big stink. You can't refuse. And so we were asked, those of us who had seen what was going on were asked to get into it. And I guess they felt like maybe some of us would speak up a little louder. So I entered the fray and explained what was going on. And then all of a sudden I got from an email from someone pretty high in administration, something I had mentioned, and they, the whiteboards that were in the rooms were very new. We didn't know why. And they came back and said, wait, they weren't supposed to cover the whiteboards. They were only supposed to cover the chalkboards. I said, well, they covered them all. And it's not, if they had asked, we would have told them, but we were left out of the picture. So then yesterday, I happened to notice a guy was taking all this stuff down for the trash. So they came in and took off the stuff they had just put on. I don't know. Nakia, right? All right. Welcome. Anyone else come in since I called roll? Yeah, oh yeah, I got you. Yeah, when you came in. Let me make sure. Yep. Yeah. Okay. Anyone else? Okay. So anyway, here we go on our old boards again. Okay. And last night. Well, the other thing, and the only reason I didn't take this stuff off myself, I was afraid that the glue that used on the old boards might have messed up these, and it's really hard to erase. But then too, that stuff's been on here for several days since they put the other on. But anyway, we're undone now. All right. Any questions? Anything we've covered up until now? And you will be getting the quiz just a little bit later. We were talking about the other functions, cubic, square root, and reciprocal functions. We've already talked about cubic functions. We were most of the way through square root functions. That's where we left off last time. This is listening thing. When you think square root function, what comes to your mind? Domain. What's the domain of the square root function? Say again? 0 to positive infinity. You cannot take the square root of a negative number. So its domain is a little limited. How about its range? Also 0 to positive infinity, because the square root function, when you have a square root, that's understood to be a principal square root, meaning positive square root, unless you have a negative sign in front of it. So the range is also 0 to positive infinity. How about its intercepts? Does it have any intercepts? X-intercept? Y-intercept? 0, 0 is both, okay? Because you put in for the y-intercept, put in 0 for x, and you get square root of 0 is 0. Well, that gives you a y of 0, so that makes it an x-intercept as well, okay? Now, how about increasing, decreasing behavior? Square root function. Always increasing. At 0, it's 0. At 1, it's 1. At 4, it's 2. At 9, it's 3. It's always increasing. Slowly, but increasing. So it's increasing over the entire domain, which is 0 to positive infinity. Now, notice here, I mentioned this before. Usually when they talk about the portions of a domain for increasing, decreasing, they almost always just put them in parentheses. Up here, you could put brackets on these because you include 0 on the domain and the range. But here, for the increasing, decreasing, the interval, usually we just put parentheses. All right. Here is the graph of the square root function. What does that kind of look like? Half of a sleeping parabola, in fact, okay, right? Most parabolas are up, this one's lying down, okay? So, half of a parabola. All right. Why only half? Yeah, okay, the other side is negative. Well, why couldn't we have that? Besides, you can't take square root of a negative number. I learned the negative square root, you know, that kind of negative numbers would be over here. That would be, but why wouldn't you include that? Say again? I can't hear. Okay, it is always increasing, but that's because we only choose half of it, wasn't it? I mean, it's sort of a circular argument. Why wouldn't you include the other half of the parabola? Plus or minus the square root of that?
You see a different equation.
Okay.
The equation would have to be x squared.
Okay. The big issue, would it be a function? Would it?
No, that's the
Oh, it fails the vertical line test. Okay, you're absolutely right. Okay, good morning, Vietnam. Okay, yeah. It would fail the vertical line test. So that's why the other reason, all your reasons were correct, but that's the other one. It wouldn't even be a function if you included the other half. Very good. All right. Now let's go to the reciprocal function. Reciprocal function is f of x is equal to 1 over x. Would you consider that a polynomial function? Very good, okay. Why not? All right. If you wrote that in exponential form, what would that be? F of x is equal to? Okay, f of x is equal to y. All right, we got that one. Okay. But what would this side be written in exponential form? What's the exponent for that x? It is down there. If you wrote it, f of x is equal to x to some power, what power would that be? To the what? -1. Excellent. Okay? And remember what the rules for it to be a polynomial? Your exponents can only be positive whole numbers. No fractions, no decimals, no negatives. So no, that is not a polynomial function. Okay? Now, but it is a function. Okay? Now, what are some things you notice about this? As in, where is that variable? Okay, on the bottom, in the denominator. It cannot be 0. Fantastic, okay? Because you can never divide by 0, okay? So, what does that say about the domain of this function? It cannot include 0. It can be any negative number from negative infinity up to 0, but cannot include 0. And then from 0, right past 0, I mean just right at 0, but not including 0 all the way to positive infinity. So that is your domain of the function. All right? So you can put negative numbers here. You can put fractions here. You can put decimals there. You can put rational numbers, irrational numbers. You can put anything except 0. Okay? what would that do to your range, which is the f values? Any restrictions there? It can't be 0 either. The only way y could be 0 if you had 0 in the numerator, and guess what? That's not a 0, it's a 1. So the only way you can have a fractional form, a rational expression that has to be 0 is if the numerator is 0. And that one can't be. So it also, for sort of a different reason, is such that but every other number it could be. Okay? So its the range is also negative infinity up to 0, but not counting 0, from 0 to positive infinity, but not counting 0. Okay. Now, you almost have to see oh, no, you don't. How could we talk about even and oddness here? How would that work? Say again? Okay. That works for polynomial functions. And this one it kind of works for too, but I wouldn't trust it always. That's a rule for polynomials. Okay, this is not polynomial. But what is the rule for how you test for even and oddness? Consider not x, but say again? Minus x, exactly. What happens if you put a minus x here and a minus x there? What do you get? 1 over a negative x. How does that compare to 1 over x? Exactly the opposite. And if it's exactly the opposite, what kind of function is it? Odd. So sure enough, this is an odd function. Now, since it's an odd function, what does that tell you about its symmetry? Odd functions are always symmetric about the origin, not the y-axis. Even functions are symmetric about that. So it is an odd function, and it is symmetric about the origin. Those should be together. They're one and the same. Okay, how about the x-intercept for that? Or would you rather do your y-intercept first? Say again? You can't do either one because we excluded 0 from both x, domain, and the range, so it can't have either an x or a y-intercept. It has no intercept. First one we run into without an intercept, isn't it? All right, good deal. Oh, and how about its behavior? Increasing, decreasing behavior. What about it? What does it look like? It's helpful to have the graph of it. We're going to do that on the next slide. But how would this look? When x is close to 0, it can't be 0, close to 0, like x equals, say, 0.1. It's not real close to 0, but sort of close. What would f of x be then? How's another way to express 0.1? Say it for me. What is 0.1? You solve. X equals 0.1. How would you read that? Not 0.1, but 1/10, exactly. So write that as a decimal. A fraction. 1 over 10. And if you reciprocate 1 over 10, what do you have? 10 over 1. So when x is 1/10, pretty close to 0, the y is 10. You get closer to 0, and guess what? The y goes even higher. Like 100th would be 100. 1,000th would be 1,000. 1 millionth would be 1,000,000. Okay? So what's it doing? It's increasing as you go into 0, but we always go left to right. What's it doing then? It's decreasing like crazy. What happens when you get to 1? X equal 1 is 1. X equal 2. Okay. 1 over 2, which is 1/2. 3 is 1/3. 4 is 1/4. What's it doing? Decreasing all the way. Now let's go over to the other side. What happens if it's a -1? X equals -1, what do you have here? -1, okay? What if that's a -2? -1/2. So as it's coming in, it's getting less. So what's it doing there? Decreasing also. So it's decreasing to the left, decreasing to the right. Stand up, sit down, fight. No, that's a different thing. Okay, so it's decreasing throughout both of those intervals. But it has a huge disconnect at 0. Enormous disconnect. Here's the graph of it. This is what we were just describing. As you get close to 0, it's going very, very high. For large numbers, it's going very, very small. That's 1, 1 there. -1, -1 here. Very large negative numbers. It's again close to 0. Very large, very negative numbers very close to 0 get extraordinarily negative. Okay? So when I say a huge disconnect at 0, it's going to negative infinity there, positive infinity there. You can't get much further from each other, right? Huge disconnect at 0. There's how it looks. Boy, if we had the graph, we could have answered all those questions pretty easily, wouldn't we? Decreasing function here, decreasing function there. But in other words, a reflective across the origin, therefore odd function. Yeah. Any questions? Reciprocal function. All right. Now there's one other, and we've already sort of talked about these before, 1.4 I believe it was, piecewise defined function. And there's one special kind of these called the step function. There's several kinds of step function. We'll look at a few of these. Okay? Functions whose graph resembles stair steps are known as step functions. Really creative of how we name these things. Okay? The most famous, it's really famous too, of the step functions is the greatest integer function, which is denoted by this symbology. Okay? Kind of looks like an absolute value, but it's not, okay? It's greatest integer, okay? And it's defined this way. F of x is the greatest integer in x. That's how you read this, just like if that was squared, you'd read it x squared. You read this, greatest integer in x. Now, what do we mean by that? It's the greatest integer less than or equal to that x. So give me an x. 2. What's the greatest integer? The largest integer less than or equal to 2. 2 is equal to 2, right? So give me another x. Not an integer. Not that hard. That's an integer. Say again? 7/8. Very good. What's the greatest integer less than or equal to 7/8? 7/8 is not an integer. Greatest integer less than or equal to 7/8. Okay, do this. Picture the number line. Okay? 7/8 is somewhere right about there. What's the greatest integer less than or equal to 7/8? 0. Very good. Excellent. Give me another integer. I mean, not integer. Give me another x. Not an integer. And this time, a mixed number.
68 3/4.
Say again?
68 3/4.
68 3/4. Is that what you said? Okay, 68 3/4 is somewhere out there. Somewhere out there. What's the greatest integer less than or equal to 68 3/4? 68, exactly. Okay. So here's a little hint for positive numbers. For positive numbers only, lose the fraction, lose the decimal. You know, that's the greatest integer in that number. But what happens if we go to negative? Give me an x that's negative. -4. What's the greatest integer less than or equal to -4? No, -4 equal to -4. Okay. Yeah, right. Okay. So give me one that's not an integer. -3/4. What's the greatest integer less than or equal to -3/4? -1. Excellent. Because -3/4 is right over here, and the greatest integer less than or equal to that, you always look to the left, okay? And that's -1. Okay? So you see your little rule about dropping the thing doesn't work anymore. 0.75, so you can't just use the fraction. Negatives you have to go. Always look one to the left. Does that make sense? Okay, let's see what they do here. Some values, the greatest integer function are, the greatest integer in -1 is -1. Greatest integer in -1/2 is integer. -1. Perfect. Okay. So, got it. Any questions on that? All right. How about this one? Greatest integer in 1/10. 0. Greatest integer in 1.5. 1. Oh, fantastic. 1.9. 1. Fantastic. Okay. Now, how does that graph look? Okay. Here's how the graph looks. Let's just take a few of those. 1/10. You said the greatest integer was 0. 0, it would have been 0. But when you got up to 1, it would have jumped up to 1. So this is from 0 to 1. Counts to 0, but doesn't count to 1 because when you get to 1, it jumps up there. That's what makes it a step. See it jumping? Okay. All right. And it did that down here too. And that's why we call it a step function. It looks like a set of steps. Okay? All right. What's the domain of that function? All real numbers. You can put anything in there. What's the range of that function? All what? Not all real numbers. 1/2 or -1/2 or -3/4. Not in the range. You're really close. But negatives aren't whole. What do we call them? Integers. All integers. Okay. All integers is your range. Okay. How about the x-intercepts? Does it have any? What would that be? Where it intercepts the x-axis? Everything between 0 with a bracket to 1 with a parentheses, exactly, because you don't include the 1 there. How about y-intercepts? Any y-intercepts? What? 0, 0, that's the y-intercept. You're absolutely right. Is it increasing or decreasing? It's bizarre. Okay, it's constant between and then increasing at the integral value. So I don't know how you talk about that. Constant function between integers and increasing, but not continuously, at the integers. Okay, so I think we've hit all those right. Are there any others? Range, we get that. Y-intercept, x-intercept, the entire interval between 0 and 1, bracket, parentheses. Graph is constant between each pair of consecutive integers, and it jumps vertically, in other words, increasing between. So it's called it's discontinuous. Okay, that's another big thing about it. Most of the others we've hit so far have been at least mostly continuous functions, and this is mostly continuous, but it has a whole bunch of discontinuities in it. Which one of the other functions we looked at was also a discontinuous function? Only in one place. Yeah, and which one was that? The reciprocal function, exactly. The reciprocal function had one major discontinuity at x equals 0. Okay. The rest, all polynomial functions are continuous. We haven't done that yet, but I thought it would be worth stating here. Okay. And that's what that is a discontinuity at every integer. All right, so let's actually do one. Example number 2. Been through a lot of time in this section and only on the second example. Okay. Evaluate the function when x is equal to -1, 2, and 3/2. here's your function. Alpha of x is equal to, and by the way, I've got to get, oh boy, when it's offset like this, it doesn't give me my, whoops, that's not what I wanted. Ink color. All right. Doesn't give me my pen commands. Usually it's down here, but when it's offset, it doesn't give it to me. So, how do we evaluate the function when x equals -1? F of -1 is equal to greatest integer in -1. This is pretty ugly writing, okay, plus 1. And what's the greatest integer in -1? -1 plus 1 is 0. So that one would be 0. F of -1 is 0. How about f of 2? What's the greatest integer in 2 plus 1? What's the greatest integer in 2? 2 plus 1 is 3. Very good. How about 3/2? F of 3/2. That would be the greatest integer in 3/2 plus 1 would be what? 1 plus 1 is 2. Didn't know we'd be doing such high-level math today, did you? 1 plus 1 is 2. Okay? Y'all remember that? Okay, take that home and practice on that. Okay. Huh? The greatest integer in 3/2. 3/2 is 1.5.
Okay.
Right.
I was
2/3. And so that would be 1. Okay. All right. Any questions on that? So I'm going to erase all that. Have to go this way to do it. And let's see how they did it. For x equals -1, the greatest integer less than or equal to -1 is -1. So f of -1 is greatest integer in -1 plus 1. Because that's what your function was. Okay. And that would then be -1 plus 1, of course, is 0. Okay. X equals 2, greatest integer less than or equal to 2 is 2. So alpha 2 is greatest integer in 2 plus 1. Greatest integer in 2 is 2 plus 1. See, that statement up there should be right down there in between those two lines. And that would be 3. Really high-level math here. And for x equals 3/2, alpha 3/2 is greatest integer in 3/2 plus 1. Greatest integer in 3/2. Less than or equal to 3/2, but it has to be an integer. That would be 1, because that's 1.5. Greatest integer in that is 1. And 1 plus 1 is 2. Good deal. Any questions? Okay, here's how that function looks. Almost looks like the greatest integer function, but not quite, because now everything's shifted this way. But actually what it's done, it's shifted up. That's what the plus 1 does. It shifts everything that was here. I'll go back to it quickly. There, you see that? This is greatest integer function. Notice this line is here and then jumping up from there. Now, keep that one in your mind. And let's go quickly to that one. And notice the line that was here is now up there. This one that's here was up there. Everything's been shifted up by 1. That's what that does for you. This one was down here. It got shifted up. This was here. It got shifted up. Everything shifted up by 1. I'm cheating because this is the next stuff we're going to do, okay? Wanted to point that out to you. All right, see how that works? Now, my question to you, is this just some dumb math exercise to give you something else to worry about? Have any of you ever used a stepwise function? Have you ever mailed a letter? A heavy letter. Like heavy metal letter, okay. Okay. Do you pay the same thing for a heavy letter as a, oh, what do you do? And how do they do that? If it's anything between 0 and 1 ounce, and guess what? I've never mailed a letter at 0 ounces, okay, so, okay, they don't exist, okay. But, so then, the 0 is here, open circle, to 1 ounce, that's your domain, including 1 ounce, that would be, what is it, up to 48 cents or 54, I don't know what it is now. We get the forever stamps, I don't even know what first class postage, but it's some amount, okay? But then when you go up anything greater than 1 ounce, like 1.1 ounces, it jumps up to the next one, which is 78 cents or whatever it is. So yeah, you've used that all the time, okay? I know most of you probably on your phone plans now have unlimited everything, right? Yeah, okay. Not everybody, though. In the old days, you only got so many minutes, whether it was talking time or data time or something else, and then it would go up. Guess what? That's a stepwise function. Because everything between 0 and 100 minutes or whatever it was a fixed rate, and then if you did anything back that, you did another rate, anything past that, you were using step functions all the time, weren't you? Okay? All right. Now, make sure I'm not skipping anything. Yes, we are. Example 3 had something we are skipping. So what I'm going to do, this is tough. I wish I had done this. So what I'm going to do, unfortunately, oh, that's not what I wanted. Okay. All right. Let's minimize that and minimize this and minimize that. Ha, here. No, where is it? Oh, there it is. Okay, I didn't need to minimize all that. Slow, but it's coming along. Okay, we'll go from this slide. All right. Another one of my students helped me set this up because this Screencast-O-Matic doesn't have a nice, easy way to do this, so we had to do this. Hide presenter view. Now I have to go through all this again. Sorry. One more. Okay. Example 3. Sketched. Are you through? Okay. Sketch the graph of f of, and now I got to go back and get my pen. And now it changed back, so I can now do this here. And since I can't do that one, I'll do this one. Okay. Here's our function. F of x. This is a piecewise defined function, not a step function. F of x is equal to, I love this program. It's so handy to use. All right, sorry. 2x plus 3. That's for all values of x but less than or equal to 1. Quit doing that. Okay. Wow, I love this. Okay. Minus x plus 4. That's for x is greater than 1. Okay? It says graph that function. How would you go about graphing the function? There's many ways to do it. What's your favorite way of doing graphs? That would be a good thing to use. I heard him say slope-intercept form. Did I hear someone else say something? I took it here. Okay, the y-intercept first. Okay, that's not a bad way to go. Okay, and what is true about every y-intercept? What makes it a y-intercept? Say again? It crosses the y-axis. What's true about every point on the y-axis? Every point on the y-axis. Give me the coordinates for this point right here. Okay, how about this one down here? What? It doesn't just include 0. 0 is where? The x value. So if you want the y-intercept, you set x equals 0. That's always going to give you a y-intercept. So if you choose x equals 0, you got to figure out where we are, Waldo. Are we up here or are we down there? If x is equal to 0, are we up here or are we down there? Huh? Down there. Huh? If x is equal to 0, is 0 less than or equal to 1 or greater than 1? Less than or equal to 1. We're up there. Okay, so plug in x equals 0 up there, and what do you get? 3. Okay, when x equals 0, y is equal to 3. There's a point on the graph. Not a bad place to start. Okay? Now, not a bad thing to do your slope-intercept form, because how does that work? Second? Y is equal to mx plus b. So what does that tell you? M is 2. And, okay. M is 2. M is 2. And the y-intercept is positive 3. Very good. But where does this get? And then what does that tell you about the slope being 2? That's the same as 2 over 1. And what does that tell you? You go up 2 for every 1 you go over. When you go over, where do you find yourself? At x equal x equal 1, right? If you go over 1, you're at x equal 1, right? Okay? Now, that's as far as you can go with this function. So you can go backwards, but you can't go any more that way, because that includes x equal 1. So let's go the other way. What's another way to express this slope of 2? M is equal to 2 over 1. What's another way? M is equal to, for this to be equal to 2, negative 2 over negative 1. So what does that tell you? Down 2 for every, okay, over, meaning left 1. Okay, down 2, left 1, down 2, left 1, down 2, left 1, down 2, left 1. You can do it. Yeah, don't do that. Okay. All right. So this is what it looks like here. I can't get too close to that point down there because it doesn't like for me to go there. Okay. Now, how about the other side? How about the other side? That gives you all your x's less than or equal to 1. Look at that. See, all these. You got that part of the domain covered with this one. How about over there? Okay, x is greater than 1. How do we graph that? Ah, plug it in, plug it in. I thought some of you were going to say a t-table, but no one said that, huh? Y'all never graph by using, give me an x, calculate the y. Y'all don't do that, huh? Yeah, of course you do, okay? You don't have to if you don't want to. You just said 2. And which one do we use if we got x equal 2? The bottom one. And what would that give you? 2, okay? So x equal 2, y is equal to 2. Next. And what do you notice about that function? You're not interested in the y-intercept too much anymore because it can't get over here to the x-axis. But what do you notice? Slope is? Negative 1. So what do you do from here? Down 1, right 1. 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 Have we graphed this function? Whoops. That's at least part of it. What are we missing? Okay, let's back off. What's the domain of this function? All real numbers. What's the domain of our graph here? Everything this way and everything that way. We've left off this. Those are real numbers in there, aren't they? So what do we do with those? Huh? Okay. We'll put a parentheses, but yeah. But what will it do about the graph for the numbers here? Okay? Here's how we cheat. We act as if we're going to do a 1. You know it can't be equal to 1, but let's go and plug in a 1. What would that give us? 3. But guess what we put at the 3 rather than a filled-in dot? An open circle, exactly. And now you can extend this all the way there. So that's what you do on the side that doesn't have the equal sign. Go on and put it in, but put an open circle there. If you do have the equal sign, fill in the circle. Don't go any further, but go only whichever direction it tells you to go. But when you don't have the equal sign, go on and plug it in anyway, but leave that open. Does that make sense? And then your graph goes up from there. I know that's pretty, but you can probably do better. Okay? Maybe. Okay. All right. See how to graph that? All right. There's a checkpoint there. Not a bad idea to go home and practice on those, or even go to the library, or go to another classroom, do something, and make sure you understand those. Okay. Now, I think what I have to do, no, that's not what I do here. I think I escape here and discard and go back to this one. All right. Now, let's talk about the parent functions. Okay? These are the ones that give all the orders and don't have to do anything. No, that's not it. What do we mean by parent functions? And now I'm going to have to go through all this again. I really love this package. Okay. Okay. Finally get something. Okay, the parent function. Now it's shifted over there again. I don't know why. Okay. Parent functions. These 8 graphs, 7.5 graphs or something like that, you can't see that, shown below represent, these are the ones we've already done, the most commonly used functions in algebra, or at least the simplest form. Here's the first, called the constant function. It is a linear function, but what's special about that line? It's what? Horizontal line. And usually when we're talking about lines, what form did you like? Yeah, you said slope-intercept form, right? So what's the intercept on this one? Yeah, x equals 0. Y is equal to? C. Okay. Yeah, whatever it is. 1 point whatever. Yeah, C. Okay. What's the x-intercept? That does not have one. What's the slope? 0. Different from not having one. It has a slope, but it's a 0 slope. It neither goes up nor down. Okay. So there's your constant function. Another linear function we do a fair amount with, and that's the identity function. That's f of x equal x. In other words, what was f of x? You said earlier, y is equal to x. So they're identically the same. Whatever x is, y is the same thing. X equals 68 1/4. Y is equal to 68 1/4. Okay? So the same values. Okay? Now, we didn't do this one. They just threw it in here. Here's the absolute value function. Y'all familiar with that? What is true about absolute value function? What's its domain? All real numbers. Okay? Yeah, you can feed anything in there. What's its range? Say again? 0 to positive infinity. You're absolutely right, because the absolute value can never be negative. Ever. Can be 0, but never negative. Okay? Unless you put a negative sign in front of it, and then it goes negative. Okay? What's its x-intercept? 0 0. What's its y-intercept? 0 0. Okay? Is it increasing or decreasing? okay? But it's decreasing from negative infinity to 0 and increasing from 0 to positive infinity. In fact, this half of the absolute value function, when x is a positive number, alpha of x is equal to x. That's this part. But when it's a negative number, you can't go down here, so this flips up here. Is that even or odd? Absolute value function. Or neither. Say again? Does it reflect across anything? It's an even function that reflects across the y-axis. Okay, it's an even function. How about this one? Odd function. How about this one? Say again? Even reflects across the y-axis. Okay. All right. How about that's the beginning of the square root function? Is that even or odd? Or neither? Neither. Okay, because you don't have it reflecting over anything, so it can't come over here at all. Okay, stay away. Okay, so that's the square root function. You can't see it. That's your parent function there. Okay, the next 4, or at least 3.5. This is your square. Okay. Now they're calling it a quadratic function. Actually, the better name for this is the squaring function, which is a quadratic function. This isn't every quadratic. That's the squaring function, but it is a form of a quadratic function. This is the parent function for all quadratic functions. And this is the parent function for cubic functions. Okay? Now, this one looks the least like the others. Okay? Any other constant function looks a lot like this one, just where it is on the y-axis. That's the only difference. Always that. Now, the identity function, that looks like most other linear functions, except where it is, and what the slope is. This always has a slope of 1 and a y-intercept of 0. All linear functions have other slopes and other y-intercepts, okay? But they still are straight lines. Absolute value function, you can move it around the thing. You could do all sorts of things with it there. You could either flip it over and have it down here and do various things like that. But they all look like V's, either right side up or upside down V's. Square root functions, you can move those around, but they always only go in one direction. You can flip them over and do like this, but they always go in one direction. Okay? Now, quadratic functions, you can move them up and down, move them right and left, move them around. You can flip them over and have them opening down. That's good. But they all sort of look like this. The cubic function, though, except for its parent function, doesn't usually look like this. If you had any other terms here, square terms, linear terms, and other things, what happens here is you go up and have one peak going down and going up. This just merges those two peaks together, so it goes up and then goes up. You know, usually a cubic function will have do something else in between. So this doesn't look a lot like its children, or yeah, right, it's the parent. Okay. Now, reciprocal functions look like this. You can flip them around, move them around, and stuff. So they usually look like that. And then your greatest integer function, which is a stepwise function. I guess that's kind of the parent function for all step functions and sort of for a lot of your piecewise defined functions. Familiarity with the basic characteristics of these simple graphs will help you analyze the shapes of more complicated graphs. In particular, and this is what the next section is going to be dealing with, graphs obtained from, and you can't read the word, it says translating the graphs by rigid and non-rigid, or doing something to the graphs by rigid and non-rigid transformations. That's going to be the next section. And I think that's the last slide. Okay, so let's do vocabulary. Top of page 65, vocabulary. Do you all have books, or some of you still don't? Anyone not have a book? Or do you have it online, ebook? You don't have that? Okay. I'll put it on the screen then. Okay. Let's do this. Match the following with its name. Okay. Let me say again. Right. Yeah, top of page 65. Okay. I need to take this, and I love this program because now I've got to do this again. I'm so glad they're saving us all this money. I'm not using Integrity anymore, using Screencast-O-Matic. It's so much fun. Okay. Actually, I can do this. No, I can't. Okay. All right. Match each function with its name. The first one, f of x, is equal to this strange looking symbology here. What's the name of that function? Greatest integer function. Very good. How about this one? What do we name that function? The what? Nope. Identity function. Very good. How about number 3? Reciprocal function. Number 4. The squaring function or the quadratic function. Parent function for that. How about this one? Square root function. Excellent. How about this one? Constant function. Excellent. How about this one? Absolute value function. Okay? Cubic function. And then they threw another one in here, not a parent function. Linear function. Okay? The identity function is a linear function, as is the constant function, but this is closer to it. But this one has slope 1, y-intercept of 0. This has any slope, positive, negative, fraction, decimal, rational, irrational, whatever, and any y-intercept, positive, negative, fraction, decimal, rational, or irrational. So that's your linear function. Very good. Fill in the blank. The constant function and the identity function are 2 special types of blank functions. Say again? They are parent, for sure, but all those others are too. But what's special about constant and identity? What type? They're what? Linear functions. Excellent, excellent, excellent. Okay. And they are all parent functions. Okay. So, skills and application, do either 11 or 13, or both. Any of the odds 15 to 25. Either 27 or 29, or both. Either 31 or 33, or both. Any of the odds 35 to 39. Do 41, the only one like that one. And then do any of the odds 43, either 43 or 45. No, I'm sorry. Any of the odds 43 to 47. Okay? Now, exploration, not a bad thing to look at those and do those as well, including the true false, at least the odd one there. All right. Now, at this point, I do want to make sure all of you have a copy of the first quiz. A few of you hung around last time and got copies. The copy machine was very slow last time. I think it was heavy. So if you didn't get one before, take one now, and I'm going to come back around. Did you get one before? Okay. You got one before. Did you get one? Did you get one? Oh, sorry. Okay.
What is this big?
You got one? Now, this does have a graph on it. So if you don't have graph paper, I've got some graph paper. I hope I have enough, but if not, I can make more easily enough. So I've got to find it. Here it is. Okay. So if you need graph paper, you do. Okay, who needs graph paper? All right. Need graph paper? Anyone else need graph paper? All right. You only get one. You can get two, though. Okay, anyone else need graph paper? Good deal. Is that the end of class? Just because they're giving out the quiz doesn't mean it's in the class, does it? Is it out of time? Okay. So sad. But I guess true. Okay. I don't know what I did with the rest of them, but we'll find them later. All right. See you Thursday.